Chapter 1, Section 3, Physics Talk, Understanding Motion. As part of your chapter challenge, you need to describe the motion of a motor vehicle while you are driving. You are expected to explain what factors affect following distance, braking distance, and the total stopping distance. One factor that affects all of these is speed. Speed is the distance traveled per unit time. In the investigate, you represented constant speed, speed that does not change over a period of time, by using strobe photographs, distance time graphs generated by a motion detector, and an equation. Model 1. Describing motion and speed using strobe photos. As you discovered in the investigate, there are many different ways to describe motion. One way to show motion is with the use of strobe photos. A strobe photo is a multiple exposure photo in which a moving object is photographed at regular time intervals. You use the diagrams of strobe photos in the investigate to represent different speeds. The illustrations below show constant motion at a slow speed on the top and constant motion at a fast speed on the bottom. You saw that when an object is moving at a slow speed, the distance between the objects is less than when the object is moving at a fast speed. This makes sense because at a slow speed, the object travels a shorter distance during the same time than at a fast speed. Model 2. Describing motion and speed using an equation. In the investigate, you also used an equation to describe speed. The average speed of a vehicle is the ratio of the total distance traveled to the total elapsed time. Average speed equals distance traveled divided by time elapsed. Is there an equation? Physicists try as much as possible to describe things they observe mathematically. They use equations to express relationships. Equations are precise and give you a lot of information with a few words. Equations can also help you to make numerical predictions of what will change under new circumstances. Student scientists, just like you, often ask, is there an equation? Whenever possible, active physical science will provide you with an equation you can use. The equations that you use are summarized for you at the end of each chapter. Average speed equals distance traveled over time elapsed. You could also say speed equals distance over time. Okay. This equation can be written using quantity symbols, where VAV is average speed. Okay, so there's your average speed. Distance is a change in position or total distance traveled. T is change in time or elapsed time. The Greek letter delta is often used in science to mean a change in. In this section, you will be dealing only with situations in which you are given total distance traveled and elapsed time. So it's speed equals distance over time, or speed equals distance divided by time. Okay. Symbols for physical quantities. Symbols for standard units are unique and precise. There is only one symbol for each standard unit. For example, M stands for meter and S stands for second. The same standard symbol is used in every language. When writing equations in science, There is also a need for other symbols. Symbols are needed for quantities such as distance, time, or speed. These symbols are not part of the System International, which is the metric system. They are also not always unique. For example, V can stand for volume or voltage as much as possible. Scientists try to use standard symbols for quantities. However, the standard symbol V only stands for volts. When writing equations, you should use the same symbols used in active physical science. To distinguish the two types of symbols in printed materials, sloping italic type is used for quantity symbols, and upright or Roman type is used for standard symbols. Sample problem 1. If you drive a distance of 400 miles, which is about 640 kilometers, in 8 hours, what is your average speed? The strategy, let me scroll down a little bit. Okay. The strategy is that you can use the equation for average speed where we said average speed equals distance over time. So your given is that the distance is 400 miles, your time is 8 hours, so you just plug these in. So you do 400 divided by 8 equals 50. So the answer is 50 miles an hour. Your average speed is 50 miles an hour. The average speed of 50 miles per hour or 80 kilometers per hour does not tell your fastest speed or your slowest speed. It only tells you that over a period of time, 8 hours, you traveled a given distance. So you traveled 400 miles in 8 hours. So you were going an average speed of 50 miles per hour. Before your vehicle started moving, the speed was 0 miles per hour. By the way, the speedometer was invented in Beloit. So the speedometer that you see in your cars, the speedometer that you see on your ATVs and snowmobiles, any speedometer that you see, that was invented in the city of Beloit. All right. Before your vehicle started moving, the speed was 0 miles per hour. When you stopped your vehicle at the end of the trip, your speed was again 0 miles per hour. During the trip, you probably slowed down and sped up as you drove along. You may have stopped for a meal. The speedometer reading at any moment during the trip is your instantaneous speed, which is the speed at a given moment. Instantaneous speed is the speed measured during an instant. Using the equation for speed to find other quantities. Equations are a powerful mathematical tool. Using the equation for average speed, you are not limited to just solving for speed. If you know the average speed and the time it took you to travel that speed, you can find the distance you traveled in that time. You can also find the time traveled if you know the distance traveled and the average speed. Speed equals distance over time. Using algebra, it follows that distance equals average speed times time, and time equals distance divided by average speed. Let me kind of scroll so you can see all this. Using quantity symbols, these equations can be written as speed equals distance over time, distance equals speed times time, time equals distance divided by speed. You can use the following helpful circle to do your calculations. So these circles are awesome because you just look at the circle and then let's say you want to figure out what time is. So time is just distance over speed. So time is distance divided by speed. Okay, what's speed? Speed is distance divided by time. Okay, what's distance? Distance is speed multiplied by time. By covering up the variable you wish to find, you can see the equation. Okay, we just talked about all this. All right. It is important to note that there is one equation for average speed, but you can write it in 3 equivalent ways. Sample problem 2. You are traveling at 35 miles an hour, about 50 feet per second, and your reaction time is 0.2 seconds, which is 2/10 of a second. Calculate the distance you travel during your reaction time. You can rewrite the equation for average speed to solve for distance traveled. All right, so what did they give us here? All right, so distance equals speed times time. Feet per second really means feet divided by second. All right, here we go. They're giving us the time, which is 2/10 of a second. They're giving us the speed, which is 50 feet per second. And we're trying to find the distance. So the solution, distance equals speed times time. So the distance is 50 feet times 0.2, and then you have your 10. When you multiply 50 times 0.2, you get 10. That's 10 feet. Calculations in units. In physics, when you do calculations, it is very important to pay close attention to the units in your answer. Notice how in the previous calculation, the units for seconds in the top and bottom of the equation cancel out, leaving feet. The unit for distance that you need for your answer. Checking to see if the units make sense is a tool that physicists use to ensure that their calculations make sense and that they have not made a mistake. Sample problem 3. In an automobile collision, it was determined that a car traveled 150 feet before the brakes were applied. If the car had been traveling at the speed limit of 40 miles per hour, what was the driver's reaction time, the time it took to apply the brakes? Witnesses say that the driver appeared to be under the influence of alcohol. Does your reaction time data support the witness's testimony? Strategy. You can rewrite the equation for average speed to solve for time. So look at what they're doing here. They're trying to find the time. Okay, time equals distance divided by speed. Well, did they give us distance and speed? Let's go up here. They gave us distance, 150 feet, which we would plug up here in the D. Did they give us speed? Yes, they gave us 40 miles an hour. So it'd be 150 divided by 40 would equal the time. So let's see what's going on here. Why are they saying 60? I thought it was 40. Hold on, let me scroll back up here. Oh, okay, here it is, 60 feet per second. We need to keep our units the same, okay? So they have 150 feet. That's why we have to use feet per second. Look at the units, feet, okay. Feet and feet per second. So the distance is 150 feet. The speed is 60 feet per second. So it's 150 divided by 60. Let's see, did they say that down here? Okay. So they did 150 divided by 60. They got 2.5 seconds. All right. Reaction time with, let me scroll down. Reaction time with distractions was measured in section 1. The reaction time of 2.5 seconds seems very slow. The driver has the reaction time of someone who could be under the influence of alcohol. That means it took them 2.5 seconds to slam on the brakes. All right, speed and velocity. In active physical science, you will often explore the same topic several times. I should have said him or her. I'm sorry. It took him or her 2.5 seconds to slam on the brakes. All right. In active physical science, You will often explore the same topic several times. Being exposed to the same topic at different times and in different situations helps you learn and understand the topic better. The difference between speed and velocity will be explored at different times in this book. Velocity will also be explored in greater depth in later chapters. A term you often hear is used when talking about speed is velocity. Velocity is a speed in a given direction. Velocity always includes both speed and direction. Model 3. Describing motion and speed using a distance-time graph. Okay, so there's your distance on the y-axis, there's your time on the x-axis. It kind of looks like it's speeding up. All right. You investigated how to represent motion with strobe photos and with a mathematical equation. A third way to represent motion is with graphs. Graphs are a visual way to represent data. The graph at the right shows an automobile traveling at a constant speed of 50 miles per hour. Okay, that kind of makes sense because every hour they've traveled 50 miles. Now with 2 hours, they've traveled 100 miles. They're going 3 hours, they've gone 150. They've gone 4 hours, they've gone 200. All right. Notice that time is on the x-axis and distance is on the y-axis. By reading the coordinates on the graph, you can see that the automobile reached the 50-mile position at the end of 1 hour, the 100-mile position at the end of 2 hours, the 150-mile position at the end of 3 hours. Let me scroll up a little bit because it's still talking about this. It's still talking about this graph. It is quite unrealistic to assume that an automobile could keep this speed of 50 miles per hour for a full 3 hours. If it did, however, you can see that the distance-time graph forms a straight line. Anytime an object moves at a constant speed, the distance-time graph is a straight line. So if you were on a straight desert road, a straight flat desert road with your cruise control on and there were no stop signs or no stoplights, you could do that constant speed for 4 hours. In the Investigate, you used a motion detector to generate graphs to represent your motion. You can determine the general motion of a person, a vehicle, or any object by reviewing a distance-time graph. Look at the following graphs. All graphs have the same time and distance scales. Graph A, a person is at rest. As time increases, there is no change in the position of the person. The person is standing still. Graph B, a person is traveling at a slow speed. As the time increases, there is a small change in the position. Graph C, a person is traveling at a fast speed. As time increases, there is a greater change in the position. Notice that the slope of the graph indicates the speed of the person. A slow speed has a gradual slope. A fast speed has a steep slope. No motion has a zero slope. The graph of a person at rest is a horizontal line with a slope of 0, representing a speed of 0. Graph D, a person is traveling in the opposite direction of the person in the previous graphs. As time passes, the change in position is in the opposite direction. I kind of think this is how the GPS on our phones work a little bit. All right, graph E right here. A person is changing speed. As time passes, the change in position is increasing for each second. Notice that a changing speed is a curve on a distance-time graph. In the Investigate, you notice that walking toward the motion detector produced a slope in one direction. Walking away from the motion detector produced a slope in the opposite direction. The slope was 0 or close to 0 when standing still. Speed and the slope of a distance-time graph. You compared speeds by looking at the slope of lines on distance-time graphs. You can also use the slopes of distance-time graphs to obtain a quantitative number value for speed. The slope of a line is the rise, change along the y dimension, divided by the run, change along the x dimension. If you look at the distance-time graph, the rise is the distance covered and the run is the time taken. So here's what they're saying. The rise is the distance covered and the run is the time taken. All right, let me scroll back now. Okay. Distance divided by time is the equation you use to calculate speed. Slope equals rise over run, speed equals distance divided by time. The measure of the slope of a distance versus time graph is equal to the speed of the object. Okay. More about the SI system. Units for measuring speed and velocity. In active physical science, speed and velocity, or speed in the direction of motion, in the classroom is measured in meters per second. Note that the unit for speed or velocity is made up of a combination of the two SI base units, meters and seconds. These are called derived SI units. Other units can also be used for speed. For example, highway speeds could be measured in kilometers per hour. The movement of Earth's crust could be measured in centimeters per year. Kilometers and miles. Okay, now we get to scroll down because I believe we have a new focus here. Okay, kilometers and miles. Highway signs and speed limits in the United States of America are given in miles per hour, or mph. Almost every other country in the world uses kilometers to measure long distances. A kilometer is a little less than 2/3 of a mile. 1 kilometer equals 0.6 miles. Kilometers per hour is used to measure highway driving speed. For shorter distances, such as stopping distances and experiments in a science class, speed is measured in meters per second. You will use miles per hour when working with driving speeds, but meters per second for data you collect in class. It is important to be able to understand and compare measurements. There are mathematical conversions that can help you convert from miles per hour to kilometers per hour and meters per second. To help you relate the speed with which you are comfortable to the data you collect in class, the chart at the right gives approximate comparisons. It shows standard speed limits for the United States and Canada. Okay, so they're calling the United States imperial and Canada metric. This is also SI. Miles per hour, feet per second, and kilometers per hour, meters per second. Speed and the Doppler effect. Driving safely is everybody's responsibility. Part of safe driving is obeying the speed limit. All roads have a speed limit. This speed limit is posted for some roads, but not for all. As a driver, you must know the speed limit of roads without a posting. Most people are aware that going too fast is dangerous. An accident at a high speed results in much greater damage than at lower speeds. However, traveling too slowly can also be dangerous and result in accidents. You can find out if you are speeding by reading the speedometer in the car. You can also calculate the speed by using posted mile markers on some roads. If you measure the time it takes your vehicle to travel between 2 mile markers, you can find the speed of the vehicle by using the equation for average speed, which is speed equals distance over time. You can also get a sense of the speed of a passing vehicle by listening carefully to the sound of the engine and the tires on the road. Sound travels in waves. The shorter the wavelength, the higher the pitch. The longer the wavelength, the lower the pitch. As you stand on the side of a street, you can hear the change in pitch of a vehicle as it moves past you. In auto racing, The shift in pitch is quite noticeable. As the race car approaches, you hear a high pitch, and as the car departs, you hear a low pitch. This change in pitch of sound is indicative of the speed of the car. The driver of the vehicle would not notice any change in pitch because the driver is traveling along with the source of the sound. The change in pitch is called the Doppler effect. It is named in honor of Christian Doppler, an Austrian physicist and mathematician who was one of the first to analyze this phenomenon. He noticed that the pitch or frequency of a train whistle was higher as the train approached and lower as the train departed. To help you understand why this effect occurs, look at the diagrams on the following page of a stationary source of sound and a moving source. Okay, let's see if we can look at the diagrams while I read this. We're going to have to get to them a little bit later. In the first diagram, the sound source is stationary. A person standing at position X and one standing at position Y would hear the same frequency of a sound. In the second diagram, the sound source is moving to the right. As the sound waves approach position Y, they are closer together than if the source were stationary. Let me scroll down a little bit to see if we can read this as we look at it. Here we go. Okay, so here's what they're talking about. A person at this position would hear a higher frequency sound. The source is moving away from position X. As the sound waves approach that position, they are farther apart. A person standing at X would hear a lower frequency sound. You will learn more about sound waves in a later chapter. So let's examine this chart for a little bit. Here's the source of the sound wave. So if you're sitting in your car driving, this is where you are right now. But then there's a person, this indicates a person standing here, a person standing here. Again, that would be the source. So the engine, the tires, the moving parts. When there's a longer wavelength, there's a lower frequency. Shorter wavelength has a higher frequency. So as it gets closer, so as the car or the train or the plane or the ATV or the snowmobile gets closer, it has a higher pitch. The further away, lower pitch. Okay. Is there an equation for the Doppler effect? The equation relating the increased frequency and speed of the train is given by, all right, here we go. Frequency equals frequency of the train at rest times the speed of sound divided by speed of sound minus speed. So I would almost use parentheses. I would solve that within parentheses, and then when you get what that is, then divide it by what this is in parentheses, and then that would equal the frequency. And, Miss McEntee, Mr. Harrow, Miss Scoville, you can really reach out to any of us to help you with this stuff. So, okay, here we go. Using the Doppler effect for sound waves is not an effective way of measuring a precise speed of a moving vehicle. Police use radar guns that use the Doppler effect for microwaves. The police radar sends out microwaves of a certain frequency. These microwaves reflect off the vehicle. If the vehicle is stationary, the microwaves have the same frequency as the emitted microwaves. Okay, so the reflected microwaves have the same frequency as the emitted microwaves. If the vehicle is moving toward the radar gun, the reflected microwaves have a higher frequency. If the vehicle is moving away from the radar gun, the reflected microwaves have a lower frequency. The emitted frequency and the reflected frequency are compared electronically, and the radar gun determines the speed. The Doppler effect is also used to measure the speed of galaxies at huge distances from Earth. The frequency of the light from the galaxies is shifted to lower frequencies. Astronomers interpret this to mean the galaxies are moving away from Earth. By calculating the speed of many galaxies, astronomers form theories about the birth and structure of the universe. Theories, it says. The physics chem talk may also include the elaborate phase of the 7E learning cycle. The elaborate phase provides an opportunity for you, the elaborate phase provides an opportunity for you to further your knowledge to new areas. Reaction distance. While you are deciding what to do in any given situation, your automobile, in the meantime, is traveling over the ground, possibly approaching traffic or pedestrians. Okay, so this is really important, guys. Let me read this again. Reaction distance. While you are deciding what to do in any given situation, your automobile, in the meantime, is traveling over the ground, possibly approaching traffic or pedestrians. At a given speed, the time it takes you to respond to a situation corresponds to the distance that the automobile travels. This distance that your automobile travels until you respond is known as the reaction distance. Okay. In sample problem 2, you saw that for a reaction time, what kind of car? That looks like I don't know what that is. Maybe if you know what it is, you can email Miss McEntee or email Mr. Harrow if you know what type of vehicle that is. All right, in sample problem 2, you saw that for a reaction time of 0.2 seconds, your automobile would move at 10 feet if the automobile were traveling at 35 miles per hour. A longer reaction time increases the distance you travel before you even begin to brake or turn. The longer your reaction time, the greater the distance the automobile moves before you begin stopping, swerving, or taking other appropriate action. Your reaction time, therefore, has a direct effect on the distance your vehicle travels and the possibility of being involved in an accident. You know what? That looks like a Mazda 2. I'm going to guess that's a Mazda 2. But if you have another idea, just email me, Mr. Harrow or Miss McEntee. I think that's a Mazda 2. All right, guys.